In the general theory of relativity, the Einstein field equations, EFE, relate the geometry of spacetime to the distribution of matter within it. The equations were published by Einstein in 1915 in the form of a tensor equation which related the local spacetime curvature with the local energy, momentum and stress within that spacetime. Analogously to the way that electromagnetic fields are related to the distribution of charges and currents via Maxwell's equations, the EFE relates the spacetime geometry to the distribution of mass energy, momentum and stress. As well as implying local energy momentum conservation, the EFE reduced to Newton's law of gravitation in the limit of a weak gravitational field and velocities that are much less than the speed of light. The EFE may be written in the form, where the uppercase G mu nu is the Einstein tensor, the lowercase g mu nu is the metric tensor, T mu nu is the stress energy tensor, lambda is the cosmological constant and kappa is the Einstein gravitational constant. The Einstein gravitational constant is defined as, where g is the Newtonian constant of gravitation and c is the speed of light in vacuum. The expression on the left represents the curvature of spacetime as determined by the metric, the expression on the right represents the stress energy momentum content of spacetime. The EFE can then be interpreted as a set of equations dictating how stress energy momentum determines the curvature of spacetime. In the Einstein field equations, the term containing the cosmological constant lambda was absent from the version in which he originally published them. For many years, the cosmological constant was almost universally assumed to be zero. More recent astronomical observations have shown an accelerating expansion of the universe, and to explain this a positive value of lambda is needed. The cosmological constant is negligible at the scale of a galaxy or smaller. Einstein thought of the cosmological constant as an independent parameter, but its term can be moved algebraically to the other side and incorporated as part of the stress-energy tensor. This tensor describes a vacuum state with an energy density ρv as c and isotropic pressure Pv as c that are fixed constants. As can be seen from this equation, the cosmological constant can be regarded as a constant energy density. This is why the cosmological constant is called dark energy. When the cosmological constant lambda is positive, the pressure P becomes negative, which means that a negative pressure is generated that pulls inward. On the other hand, under negative pressure, adiabatic expansion seems to increase the internal energy. In the cosmic case, dark energy appears to increase as space expands.